Okay, so in our last video, we looked at an example of exponential growth, and we know that we will get exponential growth if the base of our exponential function, is larger than 1. This will always be true. If the base of our exponential function is larger than 1, we'll always get this kind of exponential growth. Now let's look at an example where our base is smaller than 1, but larger than 0, because we only define exponential functions to have bases that are larger than 0. So what is an example of a base? What is an example of a base that is in between 0 and 1? Well, let's look at a base of 1/2 as our starting example. So we're going to have y equals 1/2 to the power of x as just our introductory function that we're going to investigate. So we can start with a table of values, x and y. And let's start with a negative value, -2. That's our input. So we take our exponential function, 1/2, and we apply that input of -2. Input goes in the exponent. So here we can just take the reciprocal of the base. So that's just going to be 2 now. And after we take the reciprocal, we can now write a positive exponent on that reciprocal. So now we've dealt with that negative exponent. We wrote the reciprocal of the base, and now we have a positive exponent on that reciprocal. And 2 to the positive 2 is just 4. So when we plug -2 as our input, we get positive 4. 2, 3, 4 as our output. What about -1 as our input? Well, that's just going to be our base, all to the -1 power. So we can take the reciprocal. That's just going to be 2 to the positive 1, which is really just 2. So -1 as our input will give us 2 as our output. Let's plug 0 in. So 1/2 to the 0th power. That's always just going to be 1. And let's do the first power. 1/2 to the first power is just itself. So that's just going to be, when we have an input of 1, we have an output of 1/2. And let's try plugging in 2. 1/2 all squared is really just going to be 1/2 times itself, which is just 1/4 as our output. Now we kind of have a trend going here. And we see that this curve looks pretty similar, actually, to the previous curve that we did. Let's see what we can notice about this curve. One thing about this curve is that it clearly has the opposite orientation of our exponential growth curve. So that's one thing we can notice. Another thing we can notice, actually, is that it has the same y-intercept, right? When we plug 0 in, we get 1 out. And that's always going to be true for exponential functions of this form. For exponential functions of this form, that's always going to be true, because if we raise our base to the power of 0, we're always going to get 1 out. So we're always going to have this ordered pair 0 and 1 for exponential functions of this form. Right, when we have an input of 0, we're always going to get an output of 1. So we're always going to have that ordered pair, or another way of saying that is we're always going to have this y-intercept at 0 and 1 for exponential functions of this form, whether it's exponential growth or, as we'll learn to call this, exponential decay. Now, let's try to answer some of these questions. Is this particular function increasing or decreasing? Well, as our inputs increase, what is happening to our outputs here? Well, as our inputs increase, it looks like as our inputs increase, as we go more and more to the right on our x-axis, our outputs are actually decreasing. So we can say this is a decreasing function. And all exponential functions with a base in between 0 and 1 will exhibit this behavior. So if we have y equals 1/3 to the power of x, it's going to look like the same exact shape, right? We're still going to have this sort of decreasing behavior. And I want to draw that a little bit better. We're always going to have this decreasing behavior. And we can see that there is also actually an asymptote here as well, and the asymptote is also at y equals 0, right? We can see that the outputs of this function, as the inputs grow, the outputs of this function are actually getting smaller and smaller and smaller. There is no input that we could plug into this function that would give us a negative result. And so we can say that this function is never going to go below the x-axis. And there's actually no input either that we could plug in here that would give us 0 as a result. So we're not even going to touch the x-axis. That's why we get this asymptotic behavior. It's just that the asymptotic behavior of this particular kind of function is in the opposite direction of exponential growth. We call this exponential decay. When the function gets smaller and smaller outputs for larger and larger inputs, and that happens to be an exponential function, we call this exponential decay. So we have this asymptote at y equals 0, and we also have this y-intercept at 0 and 1. And we can see for exponential growth as well, we will always have this y-intercept at 0 and 1, at least for equations of this form. We'll very soon learn that we can actually transform exponential functions. So the y-intercepts for all exponential functions won't necessarily be at the same place, but if we just have one of these simple exponential functions, y equals some base to the power of x, then for sure we will always have this y-intercept at 0 and 1, and we will always have this asymptote at y equals 0. In our next video, we're going to start to look at how to transform these functions.